Okay, Annie, we're going to start by talking about real numbers. So real numbers are any number that can be put on a number line. This is just about any number that you've run across in math class to date, actually. So you've got a number line here, even if you've got 3, 4. So let's say something like pi, and you probably know pi is 3.14. Can I put pi on a number line? Well, sure, it's somewhere around 3.14, somewhere in that neighborhood. If I had a computer, I might do it a little better, but this is a pretty good estimate of where it is on a number line. So it is a real number. The only thing that would not be a real number, something like this, square root of -4. That would not be real. Interestingly, though, negative square root of 4 is a number, right? That would be -2. But you can't take the square root of a negative. That causes an imaginary number, which you haven't learned yet. We may not even learn that till Algebra II. Rational numbers is something I definitely want you to know. You might remember the decimal definition of that. You might have heard this before. The decimal for rational numbers are either repeating. So what I mean by repeating decimal is something like 0.3 repeating, or the decimal is terminating. It's a fancy way for the decimal ends. And so like 0.25 would be a good example of that. Now inside the word rational is this word ratio, and that's part of the definition because basically rational numbers are just a ratio, which is kind of like a fraction of integers. So anytime you have two integers, numbers that don't have a decimal point, you can make a fraction that's definitely rational. For example, 0.25 you probably know is 1/4. 0.3 repeating you probably know is 1/3. It is no accident, but both repeating and terminating decimals can always be written as a fraction. Even a number like 7. 7 can be written as a fraction. So if it can be written as a fraction, it is definitely rational. Irrational numbers, the decimal, has a couple of qualities. So you might say it is non-repeating, does not have any pattern to it. And so not just one of these qualities, but both have to be true. Non-terminating. And so pi would be a classic example of that. Another example of an irrational number might be something like square root of 3, or square root of 2, or square root of 5. Any non-perfect square number there. Their decimal keeps on going forever, and it never, ever terminates. Just want to make sure you know integers. I've mentioned that term, and just to make sure you know the set of integers would be from -3, -2, -1, 0, 1, 2, 3, and so forth. So it goes on negative direction and positive direction forever. It doesn't have any decimal places. And so those are integer numbers. Whole numbers start counting at 0 and go up. So they have no negative component to them. This is just a Venn diagram so you can understand how this works. These are real numbers over here in this rectangle. These would be imaginary. There are two types of real numbers. There are rational numbers, and there are irrational numbers. One type of rational would be an integer. And a type of integer would be a whole number. And a type of whole number would be a counting number. Those start counting at 1 instead of 0 there. So like the number 7 is a counting number and whole and an integer and rational and real. So a number can fit into more than one category, but its most specific category would be the best way to name it. We're going to graph some of these numbers on a number line. So I'm going to make a little number line here. There's 1. There's -1. I'm going to go ahead and split this into about 9 different ninths here. I'll try to. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 7, 8, 9. Okay. So I've got my number line here. Split it into ninths since we're dealing with ninths here. And I'm going to put these numbers on the number line. So 1/2 would be, let me just go ahead and try to move that, be somewhere over here-ish. We'll try to put it there exactly in a minute. 1/9 might be somewhere right here. -4/9, somewhere around there. And -7/9 somewhere around there. So we could even put points, let's see, 1, 2, 3, 4.5. That would be 1/2. 1/9 would be there, -4/9, and -7/9. So I think a number line can help us to order things from least to greatest. So least means smallest to biggest, and so these would be the numbers in order. These 4 numbers in that order would be from smallest to biggest. Same thing here. We're going to try to order these numbers, put them in order from least to greatest. So here's 0, here's 1, and I'm going to split this into fifths, I guess. 1, 2, 3, 4, 5. And so approximately, let's try to put these numbers where they should go. 4/5 might be somewhere around there. 0.1 is hard to put on here, it looks like, but somewhere in between, this would be 0.2, so between 0 and 0.2. Square root of 3, not sure exactly. We might need to get a calculator out to kind of figure this out. And square root of 2 might be a good idea to get a calculator for this stuff. So I'm okay with you using a calculator. So if you hit your scratch pad button right there in the corner, right on your calculator page, just go ahead and type in square root square root of 2, and I'm going to hit Control Enter to get the decimal there, and I'm going to type in square root of 3 and hit Control Enter to get the decimal there. So 1.41 and 1.73. Let's see if that helps. So 1.41 and 1.73. So I didn't go far enough over here. 2 is somewhere over here. But what I do know is the order now. This square root of 3 would be somewhere over here. Somewhere over here would be square root of 2. And so I definitely now have them in order. And so graphing them on a number line can definitely help you, give you a good estimate. By the way, if you didn't know what this was, that is 0.8, you could certainly type that in your calculator and get that decimal. I think that's something you failed to do on the, and maybe it's just because you didn't think you could use your calculator at all, and that section would have been a good section, especially involving the square roots, where calculators would have been nice to be able to use. We have a repeating decimal here, and there is a way to do this by hand, which is really what I'd like you to do for this. And so to do that, we're just going to set this as x equals 0.8 repeating. We know that 8 goes on and on and on here, but we don't have to list that. But we're going to do some fancy algebra to solve this problem and get rid of that repeating decimal. And so what's kind of neat is if I can just move this decimal place over one place, I would be able to subtract from that. And so to move it over one place, I'm going to multiply by 10. To do that to both sides to be fair. So I multiply the left-hand side of this equation by 10. And if I multiply the right-hand side by 10, I get 8.8 repeating. And that's really helpful because now if I subtract these two equations, 10x minus x is 9x. And 8.8 repeating minus 0.8 repeating, the 0.8 repeating just falls right off. It just kind of cancels out, if that makes sense. And you're left with 8. Divide by 9, there's a very simple equation there, and you get, that cancels, x equals 8/9. By the way, you can tell this is a rational number, can't you? So this simplifies to be 0.8 there. And this is a little bit harder. The goal here to start with, you really want that decimal, wherever the decimal point is, you want the repeating decimal to be just to the right. So I really want to start on this one with my decimal point right there. So I'm going to start by writing 10x equals 3.7 repeating. And so by doing that, now I start here. I want that decimal to fall right off. So I'm going to multiply to move it over one more space. I'm going to multiply by 10 more. So 10 times 10 is 100. So 100x equals 37.7 repeating. When I subtract, I get 90x equals 37 minus 3 is 34, and 0.7 minus 0.7 is gone. Divide by 90, divide by 90. You get x equals 17 45ths when you simplify that fraction by dividing by 2, canceling out a 2 there. In this page, I'd like to be able to put an inequality sign between these two numbers, and so it might be a good idea to use a calculator at this point. So 7/13 and 9/17. So 7/13 and 9/17. And so you can easily see, well, let's see if it typed in 9 divided by 17. There we go. They're very close, actually. We have 0.53 and 0.52. So, looking back at that, 0.53 and 0.52, and I could go more digits, but really, and that's just approximately equal to that. I know they're not exactly equal. And so you can see which one is bigger, and if you remember from a long time ago when you first learned inequalities, the alligator opens up to be at the alligator's mouth right there. It opens to the bigger number, it points at the smaller number, and 0.52 is definitely smaller than 0.53. So we're saying 7/13 is greater than or bigger than 9/17. And so that would be the way or the method that you use to do this. So you could type 12/5 in your calculator and you figure out that's equal to 2.4. And so I hope you realize this really represents approximately 2.444 repeating. And if you go to the next, 2.4 is of course exactly the same, but then when you add this second decimal there at the hundredths place, this becomes the bigger number. And so again, it's going to be a greater than sign here. And so that's how you approach those types of problems.